Well, good afternoon, and thanks for your patience. But welcome to this lunch-hour lecture. I'm very pleased to introduce Helen Czerski to you, who's going to talk about, as you can see on the screen, bubbles in science. Thank you very much.
It sounds very serious, doesn't it, the scaling of reality? What I'm going to talk about is, it's not really it's in a comparison. It's a few ideas that I'm thinking about more and more as time goes on, I think we should think about. And so there's not a huge amount of science content, but what I am going to talk about is this problem of how you get from small, simple things to big, complicated, messy things. And it's one of those problems that everyone would really love to sweep under the carpet. Can we just pretend it doesn't exist, you know? And I think we should face up to it because it's going to become a bigger and bigger problem. So I started thinking about all this. So I'm a bubble physicist. I very happily reside in the Department of Mechanical Engineering here at UCL, but they still let me do physics, so it's all right. But along the way, my PhD was in explosives physics, and then I sort of crept into oceanography by the back door. And at some point, as a postdoc, I found myself at the University of Rhode Island, which is a very small state on the east coast of the US. And I was in this department of physical oceanographers just after having spent a year studying bubbles in the lab. And I was in this department, and they were lovely people. We never seemed to be really quite on the same wavelength. And after a while, about 4 months, I worked out that it was because of this. And in fact, the first talk I gave there, I showed exactly this slide. So because we have to have scales, because we're talking about scales, this bottom scale is a time scale. So it goes all the way, it's a log scale. It's very convenient. So we can go all the way from microseconds over here, all the way up to several years over there. So that's what's on the bottom. And then up the side, we've got from microns, so millionths of a meter, all the way up to the size of a planet. So this is kind of the scale of science, unless you're an astronomer. Everybody else is on this scale somewhere. And I realized that the reason that I couldn't talk to my colleagues is that we were separated by 13 orders of magnitude in both time and space. I studied bubbles breaking apart and joining together, these processes that happen on less than a millisecond, and they're very, very small, and they were all thinking about Rossby waves and things that took years and go around the entire planet. And there was it was like, they couldn't really have a conversation. And in The Lord of the Rings, you may remember these Ents. Treebeard was an Ent, which was a sort of very tall, slow tree, who did things very slowly and was very puzzled by the hobbits because they were sort of running around very quickly, whooshing about. And at some point in Lord of the Rings, and I did read all of the second book again just to find this quote, definitely in there, Treebeard says to the hobbits, "That doesn't make sense to me, but then again, you are very small." And there's this problem, right, in science, is that quite often it's the big things that matter, but it's the small things that kind of make things tick, and we have to sort of connect these things together. And so that's all right. So this is my job as a bubble physicist, and I'll talk a little bit about what I do with bubbles to set the context for this. But, oh, and excuse me coughing. I've got a cough that won't go away. There's a similar problem in how we talk about science, but the axes are different. I promise there's only really two graphs. You'll get used to them. So along the bottom here, we have number of people, also on a log scale, which is you can sort of proxy for complexity, right? How hard, how complicated was this? How many people did it take to do it? And up the side, we have the most important scale as far as everybody that isn't a scientist is concerned, and that is, why should I care? It's always the first question. It's a very good question. So that, I'm going to have to invent some units for that, but that goes up the side. And so here's the problem, that obviously what we want, we, society, politicians, people who talk about science and sometimes give us money, what they want is things that we care about a lot. So that's all right. But the problem is that the way we tell the stories of science is all stories that are in this very odd corner up here. They're stories from the past. So they're stories like Edward Jenner and the smallpox vaccination. One person and an awful lot of why should I care? And, you know, special relativity, one person in the simplified story, an awful lot of why should I care? And if you're very lucky, you get out to nuclear fission there, 3 people. Awful lot of why should I care? And so the problem is that when we tell the stories of science, when we talk about scientific history, and we go, we tell the public, this is how science works, what we're doing is we're always using examples up there. So basically, that's how the public thinks that science works. They think that there's one person and lots of, why do I care? And the problem, of course, in the real world, it's not like that. We have very complicated scientific projects now. The real world has this axis that goes from down here, where a paper that I wrote on bubble coalescence as a single author, nobody cares about at all. And it goes all the way up to things like up there, the Human Genome Project, the IPCC report and CERN, where there's thousands and thousands of people involved and an awful lot of why should I care? And so the difficulty we have is that we've got to play the same connection games. When we're talking about science, we're always after sort of stories. And the problem is that stories require individuals, humans. They like one. You might get away with 3. But look at the Higgs boson. 6 people, and also thousands and thousands of people were involved in that. But we only ever really hear about Peter Higgs because we just want one person. So this is the sort of problem we have, and it's the same kind of problem. How do we get from individual little things where there are individual stories and honestly convey big, complicated things that took enormous amounts of time and enormous amounts of effort and enormous numbers of people? So this is the landscape of science communication. So what I'm going to do as we're going along is sort of compare these 2 scales because they have a lot of similarities, both in the way we do science and in the way we talk about science. And I think both have something to learn from the other one. But we'll start by setting the scientific context, and we'll use my science because it's what I know best, which is bubbles. You're not allowed to dispute that bubble physicist is a real job. Right, so if you don't know where that is, I can't help you. So let's look at this bit down here. So off the tip of Chile, on the Southern Ocean. So here's the Southern Ocean in a different view. There's this massive ocean that goes round and round Antarctica, and there's nothing to get in the way, so it goes round and round, and there's enormously stormy winds and stormy seas. And if you zoom in even more, this is a storm. There's lots of storms. They're usually going round. Like the hurricane, I can't remember what they called it, Barney or something. It's about to hit the UK, Scotland at the moment. So rotating storm, and you zoom in even further, and all the winds in that storm are pushing on the surface of the ocean, so they're pushing up waves, and eventually waves will break. And so this is what you're probably used to seeing when you think of a breaking wave, but the really good bit is underneath, and the underneath looks like this. This is my mentor in California for scale, and this is a plume of bubbles underneath a breaking wave, actually at the beach in California. And it's enormous. There's billions of bubbles in there. So there's that little sort of white patch on the top, and underneath there's all this stuff. So we've zoomed in from a planet to a plume of bubbles. But even then, we haven't got to the end of it, because if you look really closely into all of that lot, now, because of the transferring thing, I'm not sure this video is going to work, but it might play. Let's see. No, not going to play. Okay, you'll have to imagine. If it did play, that's a bubble in water. Proper bubbles have water on the outside and air in the inside. I'm not worried about those soap things. So this is a bubble in water, and what's happening to it, if you've ever been underneath a breaking wave, you went surfing at the beach, or you just waded out into the surf and you fell over, what you feel like you've been dropped into a washing machine, right? The water is pummeling you, and that's the turbulence that's generated as a result of the breaking wave. So the water all around this bubble is whooshing in lots of different directions, pushing very, very hard. And what the video shows is the bubble being stretched and squished and pushed, and eventually it's pulled apart. One bubble is pulled into 2, and so we get a new bubble. So that's really the start of my science. How do you make one bubble? What happens when one bubble breaks into 2? And somehow I have to relate the science of that all the way up to the scale of a planet, because it does matter. What happens here does matter for the planet, because there are so many bubbles. So I'm playing this scaling game. So in practice, what I do is I do lab experiments where I make 1 bubble, 2 bubbles, a few bubbles, and see what they do in different conditions. I go out to sea, so I spend time on ships and make real-time measurements in the ocean to see what bubbles are doing there. And then I kind of link the whole thing up around the back with theoretical modelling and acoustics and oceanography, and then we sort of go round and round on this thing. So in practice, that's what my job is. And it's really interesting. This is a bit of a detour, but just in case you don't believe, and I'm sure none of you are going to leave this room daring to say that bubbles aren't interesting, but just in case you were thinking of doing that. This is a bubble. Again, there's a video I can't show you, but what the bubble, imagine there's a giant drinking straw that comes sort of down here, and up here, and this is the top of the drinking straw. So the bendy straw that you've put in the drink the wrong way, the thing that we always tell children not to do, but I think adults should do it, and the kids, but adults should definitely do it. And if you blow down the straw and you blow gas up into the water, so what this thing that looks like a balloon is a bubble that's just about to form. It's just about to break away from the top of the straw. And so I did a lot of high-speed photography of this, and you can see the details of how it breaks away, which is really pretty, and I'm really sorry you don't, maybe this one will play. Let's be optimistic about this. Maybe it won't. No. Boom. Okay, so what happens is that as that neck breaks, it breaks really, really quickly. The actual breaking bit lasts about 10 microseconds-ish, 10 to 40 microseconds, and then you're sort of left with a bubble with a pointy bit, and bubbles don't like pointy bits. Surface tension forces are enormous. So that pointy bit basically whooshes back up so fast it pushes into the sides of the bubble. And the clever thing about that is that it's like a hammer hitting a bell. When the jet whooshes up on the inside, it presses on the gas on the inside, and then that gas pushes back, and then the external water pushes in again, and so you get this oscillation, and that's sound, pressure oscillation. And here is the pressure oscillation. You can see all the different letters are the shape of the bubble at all those different points. So you can see there's no sound, and then the underwater microphone starts picking up this oscillation, and that's a sound. So that's why when you blow down a straw, you hear it go blip, 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 blip. That's what this is. And by studying that signal, so we're going a long way from the planet here. Bear with me, you'll get back there. So by studying that signal, you can learn a lot about the processes that are making this bubble split off. And that means that you can use acoustics to study bubbles, and that means that you can stimulate situations that happen in the ocean. And so you sort of work your way back up to what's affecting how bubbles form and when they form. So that's a very quick version. And when it, so the top of the sea surface looks like this on a very good day. More often it looks like that one. So these are white caps. These are little white patches of foam that say there's something happening underneath. And sometimes it looks like that, and sometimes it looks like that. And so these times when this is going on, imagine the huge number of bubbles that are in there. What's happening is that they're helping the ocean breathe. They're exchanging gases across the ocean surface. When they come back up to the surface, at this particular time, the winds were averaging 80 knots, and the surface of the ocean was basically blowing away. So maybe we'll pick this one instead. So what these little white caps here, just like when you hold a fizzy drink up under your nose and you feel it spitting particles up your nose, these are spitting particles up into the atmosphere, and those help clouds form. So there's all these these tiny little bubbles. Once you start looking at them, do all these big important things. Right. So anyway, so in practice, very quickly, we'll get back to the scaling thing in a minute. I spent 6 weeks of my life on this ship, and the last 2 weeks were very, very long weeks. It gets a bit like, I like living on ships, it's fine, but we were in grey with sort of grey ocean and grey sky, and we were sitting in the middle of storms just riding them out. And after a while, it was actually better at the start when everything was breaking because there was stuff to do. Towards the end, it was a bit like I imagine prison to be. Nothing ever happened, but mealtimes kept coming round. Anyway, so this is a very old ship. It's also very creaky. This is the RV Nor, and she was the ship that the Titanic was discovered on. So she was decommissioned last year, I think, and she was 45 years old when she was decommissioned. So definitely a bit creaky. If you're going to write, but the thing, it's one of those things where you don't know whether it's better to have a creaky ship because clearly it's lasted through a lot of storms. So hopefully this one isn't going to be the one to take it out. Or do you go, well, it's creaking a bit, maybe there are better ships to be on. Anyway, so we spent 6 weeks. This is our route. That's Greenland. This is Canada and the US. So we basically did that and bobbed about an awful lot in the middle there in enormous storms and measured this bubble process. So in practice, when you're measuring the middle of the scale, this is what it's like. It's messy. Oh, and this is how you do it. This is how you measure bubbles at sea, at least if you're me. So this is a 11-meter long buoy. I stick with the American pronunciations, not only because I learned my oceanography in America, but because it's really wrong to talk about throwing buoys off the back of a ship. So this thing floats in the water, and that black bit is about where the waterline sits, and everything below that sits below the water, so it's got acoustic devices and camera and batteries, and that's all sitting below the water. And the idea is that this thing floats free, it bobs about in the storm, and waves wash over it, and then I get to detect them on all of these things. And so it floats around for 5 days, and then the batteries are flat, so we pull it back in and download the data and recharge the batteries, and off we go all over again. And this thing had a checkered life. After a while, I think on its second or third deployment, the bosun, who was he was very good, but he was very Boston. And he got slightly overconfident when bringing it back into the ship one time. So he swung out the crane in an attempt to turn it round, which was a terrible idea. Because, of course, what happened is that just at the moment where it was pointing dome to the beam onto the ship, a wave came by, tilted the ship, and the whole thing barreled into the side of the ship, demolishing the top. So we had to rebuild that. So this is top of the buoy Mark II. And then the other thing that happens at sea is that you go a bit bonkers. And it's all right, because everyone on the ship is going bonkers. We actually had a sociologist as well who was studying us going bonkers. So you know you come up with something good because she brought a notebook out and started writing. Anyway, the day the face turned up on the buoy, the notebook definitely came out. And as time went on, it accumulated eyes and whiskers and ears. And I tell you what, whoever makes electrical insulation tape should use this as an advertisement, because it went out, all those little ears, they're just foam held on with electrical tape. And it went out for 5 days in 80-knot winds, and it came back like that. I mean, yeah, it's astonishing. Anyway, so we had a competition to name it because everyone was busy going bonkers. And Inside Science and Adam Rutherford were very helpful. And so Radio 4 was suggesting names for it. It took 3 seconds for them to suggest the name Bob. It took approximately a week for Lucy Green to come up with Beyonce, which I thought was very clever. It also got called Pike because it was a stupid boy, and Del Boy the Globetrotter, and a whole variety of other very creative names. Anyway, and then we had a vote on the ship, and the boring sods voted to call it Bob because they said it looked too grumpy to be Beyonce. Anyway, so this is research at sea. And the reason it matters, the reason all of this matters, is that what happens to those individual little bubbles is affected by things like salinity and the biological crud in the water, which is the real word for surfactants, and the temperature of the water and lots of other things. So there's these tiny details which affect these bubbles in these enormous storms, and somehow they affect the weather. That's where we're going. So this is the only equation, but bear with this because it's going to come back later. So the point is there's all this complication, right? There's different types of waves, there's wind going in different directions, there's this ocean going up and down. It's all horrendously complicated. And there's different temperatures, and we don't know what the biology is in the water, and sometimes it's raining. And what we want to know is how much the ocean is breathing while all of that is going on. So what we do is we write an equation which makes it look very easy, which is what physicists do. It's like the spherical cow thing. So F on that side there, that's how much gas is going up and down. All the stuff in the brackets is just concentration difference. The bigger, if there's no gas in the air and lots in the water, you get a lot of transfer. But if they're more similar, not very much gets transferred. So that's all of that. This K thing, that's the one you've got to watch, because that's the one that holds all this complication. So all of that crud somehow is sort of tidily hidden away where we can't see it. And the thing is that it's complicated. This is how science gets done. So this is the game, the scaling game that I talked about at the start. When it comes to things like the IPCC report and the outcomes of weather models, which are right up and very complicated at the top right, this is what's going on. There's very small things happening down here, and then we sort of package them up in neat little ways that hide quite a lot of the complications. And then we package them up to take them on to the next stage, and then we package those bits up, and eventually a weather forecast pops out the top. Because it's the only way we can deal with this complication at the moment, really, in science. So this is known as parametrization. That word is also going to come back, right? And it's a way of taking a complicated thing and making it simple enough to take it on to the next complicated step. So that's science. Let's go back to science communication. So there might be a picture of it. Oh, here we go. So this, oh, no, not that one. Look at that. This one doesn't like that. I think there's a rebellion going on. This one, okay, so now we're back on this log scale. So now we're playing the game of how you get from one person down here up to complicated stuff up there. So I'm going to tell you about two stories, two examples of different things that you might want to communicate that I have myself been guilty of communicating. And one of them is to do with alligators, and the other one is to do with the grotty weather we had a couple of winters ago. So So because the BBC loved me to bits, they made me wade with alligators in Florida. And this is a swamp, and these are real alligators. They are not tame in any way. And the amazing thing about them is that they're fabulous ambush predators, and you can tell. Because I was sitting there, the cameraman was here. Look, he's got the land to run away to. I'm sitting on there in some pokey little island. And he's filming, and every time so I would say a bit, and then we'd sort of stop and reset, and I would look around. And then I'd say another bit, and then we'd reset again and look around. And every time I looked around, there were more alligators in here, until by the end, you couldn't see the water. And I'm actually not joking, you couldn't see the water for the alligator backs. And I never saw one of them move, ever, once. Anyway, so there was a reason that we were with the alligators here, and it's to do, the video's not going to play. This video not playing thing is rubbish. So I'm going to have to describe it, and you're going to have to believe me. But you can find the clip online if you're that desperate to do it. It is well worth looking at what these alligators are doing. So what happens if you're in a Florida swamp and it's 7 a.m. in the morning, because it's always 7 a.m. No one on telly is ever doing it at sensible hours. It's always 7 a.m. Or 11 p.m., one or the other. And it's very quiet. There's birds tweeting. It's all very calm and quiet and nice and bright. And then you hear this noise that is straight out of Jurassic Park. And it's not straight out of Jurassic Park 2 miles that way. It's straight out of Jurassic Park right over your right ear. And it's this enormous, deep roar, and it's loud in a way that, as a mammal, makes me feel extremely vulnerable. And then when you watch what the alligators are doing, so these are male alligators that do this, always the belligerent ones. So what they're doing is they come up to the surface, and they sink down. And then what happens just before the bellow starts is that there's this sort of little waterfall thing on their back. The sort of water starts splashing on their back. And it's a bit like, if you've ever seen one of those sort of Chinese bowl things that you set up a vibration by rubbing the handles and the water sort of spits. It's like that. So just before the alligators make the call that we can hear, they make this call we can't hear. And the consequences is splashing water. And what they're doing is super cool. So they're actually vibrating their back in the same way that they do to make the audible call, but they're doing it at a lower frequency, one that we can't hear. They're vibrating their back, and that's pushing the water, generating something called a parametric resonance, for any mathematicians and physicists in the audience, which is a really cool thing. The idea that an alligator can do that is really cool. And it makes this little splashing thing, even though the alligator's back is this far below the water surface. So it's vibrating its back down here, and the water is splashing up here. And the reason that they're doing it is that the Florida swamp is very low, it's very flat. They're making a call underwater, infrasound that's going out underwater. And both sounds go out underwater, both the very deep one and the bellow. And female alligators from far away are sort of moving through the swamp towards the sound, but when they get really close, it's so loud, it's quite hard to identify exactly what direction they're coming from. So it's thought that the splashing just makes something stick up above the water a little bit, like a little flag that says, I am here. And then they can see to get to sort of work out where they're going for the last little bit. So anyway, the other cool thing about this is that they trigger each other. So once one of them starts to do it, suddenly it's happening all around you everywhere. And the really lovely thing about that is that alligators have probably been doing this for, I can talk quite a lot about alligators, I'll stop in a minute. Alligators have probably been doing this for millions of years. Their basic physiology hasn't changed very much. And so this is kind of like a dinosaur type behavior. But this Florida swamp is very close to Cape Canaveral. And when the shuttle used to land at Cape Canaveral after flying, it would generate a really deep rumble, and the alligators would all start doing their thing. So it's an expensive way to get alligators to mate, but it's more fun than staring at pandas. Anyway, so the point about the alligators is that there might be a little, what else have we got on here? Doesn't want to talk to me. Oh, so that's the pattern. That's the pattern it makes on its back for about a second and a half. So the point about the alligators is that it's a nice, cute little story, right? They've got big teeth. They're big, scary, exciting things. It's a nice, self-contained story. 1 or 2 scientists have studied it. It's fun, right? Curiosity-driven. We love that kind of science. And this is a lot of the science communication we do. When we talk about science, is we pick the shiny, exciting things that don't really matter very much but make people happy, and we talk about them. So the other end of the scale, here we go, is a horizon that John Hammond and I presented 2 years ago. Maybe it was a year and a half ago, can't remember. And the question that the BBC Two horizon set out to answer was, what's up with the weather, right? That we'd had this winter of storms, there'd been loads of flooding, there were a couple of really, really cold winters, and there was one really, really wet one, and the question was, what's up with the weather? And if the BBC had had any idea of the true complexity of weather science, they would never have commissioned this, and we both kept very quiet. And the atmosphere, the oceans, it's the engine of the planet is an amazing thing. So you get these are, if you haven't been to this website, it's got close to real-time views at different heights in the atmosphere. Well done to those of you who've got your phone out to take a picture. Brownie points to you. So you can look up in real time and see what the winds are doing at different heights in the atmosphere. And this amazing, complicated picture with all this stuff going on. And that's the problem. It's complicated. So when you ask, why is it that there was all that rain? Or why is it that those winters were so cold? And you ask the scientists who know more than anyone else about it, it's complicated. And this is the short version of the list, right? So why was it cold for 2 winters? Well, there's meanders in the jet stream, and there's this thing called sudden stratospheric warming, and then there's a thing called Arctic amplification, and then there's El Nino that's doing stuff, and maybe the sun was doing things, and there's all these little bits, and it's just complicated. And then the list gets even longer for the wet winter, and it's a whole different set of things. And the thing is that what you're dealing with is a sort of mosaic of very complicated things, and it's not that the scientists don't know. It's that the genuine answer is that all these things kind of merge in quantifiable ways, but still they sort of merge in ways that are hard to say in a single sentence, and they produce weather. And so we had to make a program on this. And that's a much more honest view of science communication. You can think of a lot of subjects where that is much more the type of thing we have to communicate. Anyone watching that program probably came, if someone asked them next day, so why was the weather weird? They'd have gone, well, there was sort of stuff and it was complicated, right? They wouldn't have been able to say, oh, it's because, the alligator's calling and this happens and that happens. There isn't a nice simple explanation. But when you think about things like medicine and the structure of civilization and communications networks and weather and climate and, the big problems that are starting to face us in our society, they're much more like the weather problem than they are like the alligator problem. But the reason people tell the alligator story is that it's a story, and humans have this very annoying trait of responding really strongly to stories. We want a narrative through, we want a hero and a villain, we want to know that we're going from here to here. And our brain just looks at that sort of complication with the weather and goes, I can't quite put it in a framework, and so I'm just going to ignore the lot of it. So the alligator is clearly down this bottom bit of that plot, and the weather is up there. Very high on why do I care, but also involves lots of people and is very complicated. And the reason that I think it's important to talk about these complex, messy things now is that it's happening more and more. Science is getting much more collaborative. Gone are the days when you shoved a professor in a dark room in a basement for 3 years and then let him out, fed him biscuits every 2 weeks, and 3 years out he came out and won the Nobel Prize for what he'd written. Right? That doesn't happen anymore. Everything's getting much more complicated. And so the problem for science communicators is that we need to work out how to honestly represent ourselves. We're stuck with the human mind. It's a brilliant, amazing thing, and it's also extremely annoying. And so we need to deal with this complexity in the same way that the science world has to deal with the fact that if it wants to model climate, it needs to know about the bubbles and the aerosols and what the biology is doing and what temperature the ocean is, and all these little things that there's sort of no hierarchy, it's kind of flat. So here's the comparison, right, between these two things in my head. And I'm still working out what I think about this, so feel free to disagree. But this parametrization thing, where we take a thing from here and take it on one more stage, and we sort of simplify it in the process, that's like telling a story, right? When we're communicating how big things work, we build them up out of smaller things we understand, and each smaller thing we understand is like a story. We've simplified it a bit, it's got a hero and a villain, we know that this bit is more important than that bit, and we know that if someone pokes the dragon, it's going to breathe fire, right? We can sort of relate this little picture. And so the way we do, that's the way we do science, is that we go up that ladder. And whereas the way we do science communication, the way we deal with the complexity in science communication is we just go, right, we're going to tell you about owls and the sun and snow and brains and funny floating ships and cloned cats and telescopes. And we just kind of go, right, stuff. And that's another way of dealing with the problem. We live in a complex world. How are you going to convey to people understanding and information? And so here's how it goes. The parameterization is like stories. And the big data, which is the other thing people are starting to do in science, which is just like hoover up all the information we can and then say, here you go, which is all it does. I mean, you know, I'm sure there are big data scientists in the audience who are squirming right now, but it's not mechanistic science in the same way. You have to deal with it differently. And that is like what's called the deficit model of science communication. And what the deficit model is something that says, if you only knew as much as I knew, you would agree with me, right? So I'm going to tell you about cats and telescopes and frogs and clarinets. And if I tell you about enough little things, then basically you're going to end up agreeing with whatever I think. So there's this, here are the two strategies. It's a big, complicated world. Small, simple things affect big, complicated things. And there's only two ways you can deal with it. You can try and step up and map out every single step. Or you could just go, you know what, there's loads of stuff. And the human brain is good at patterns and stuff, so I'm just going to tell you stuff, and hopefully something good will happen. And the problem is, in both fields, there's just more and more and more information. So it's very difficult to organize it into little, this is why it limits the way we make TV programs a lot, because of the way the human brain works, you're kind of stuck with this linear narrative through when the real thing is all over the place. How are we doing for time? I'm probably talking for far too long. I've lost my watch. Does anyone know what time it is? In front of me, which way?
No, between the two screens.
Oh, there is a clock. Okay. It's a clock with 4 hands. Okay, so I think what it's saying is that it's 10 to 2, and that means we are going to skip ethics in the this is what science does, right? We skip the awkward bits. So there's some really interesting stuff about scientific ethics and all this, and I promise the kittens aren't gratuitous. There is a solid technical reason for having the kittens, but I'm not going to tell you what it is. So, so we're going to get through all this. So that's a thing here. So this is a quote from The Guardian a couple of years ago, 1 year ago, 1.5 years ago. Arguments are won by telling human stories, right? But the true picture is bigger and more complicated. And in the same way in science, when you publish a theory or you publish a piece of work, you're publishing something which people love elegance, right? You know, what people love is this reductionist approach to science where you kind of go clonk, you fitted the round thing into the round hole and everybody's happy, right? And that's like telling stories. And so what do we do about this? We get places, you win things, basically, if you can convert a complicated bit of science to a simple story. And sometimes that's brilliant, and sometimes there's maybe more to it. So, bye-bye ethics. So here's the thing. So physicists, of course I'm a physicist, I'm going to quote the physicist, right? So Paul Dirac epitomizes here the reductionist approach to science, which says we're going to turn everything into stories. A physical theory must possess mathematical beauty in the same way that a story must have a hero. That's what that's saying. And this is the most weasel-worded phrase in the history of the ever this is. Everything should be made as simple as possible, but not simpler. Like, it wasn't Lewis Carroll that said it, but it's exactly the sort of thing you'd find in Alice in Wonderland. Murray Gell-Mann, who was a physicist in the middle of the last century, was slightly more sophisticated in his thinking. He said, someone should be studying the whole system, however crudely that has to be done, because no gluing together, you like long sentences, of partial studies of a complex non-linear system can give a good idea of the behavior of the whole. So what he's basically saying is that there's emergent behavior. If you tie together lots of small complicated things, you get behavior you couldn't predicted from a simple model. And so this is where we find ourselves. So what we're going to do is go to the bit where, not that bit, right. So I think it's a useful comparison to make. I think it's a useful comparison to think about. I've got a lot more to say about it that I haven't got time to say now. But these two approaches can learn from each other, I think. The thing that science gets right when it's dealing with the complex picture is it's got the ambition to try, right? We complain, we're always complaining there isn't enough science funding, but someone built CERN, someone built, you know, the structures that wrote the IPCC report, the people, I shouldn't call them structures. You know, science goes, right, we're going to tackle this massive complicated problem and we're going to have a go. science communication, the world of talking about science, is much better at self-reflection than science is. Scientists go, right, we're going to do a thing, and because we're going to do it, it's definitely the right thing to do. Science communication, quite a lot of the time, is quite insecure. They're going, oh, should we have done that? Did we do that? Why did we do that? And they talk about it a bit more. And I think that science could do with a bit more self-reflection, and science communication could do with a bit more ambition. Science, obviously, is very good at recording what works and what doesn't. That's part of its job. Science communicators are much better at communicating between different groups, bringing different approaches together. And that's something that science is still learning. It's partly a jargon issue, because I hate jargon, but there's lots of it in science. Jargon, the time you hear a jargon word is the point at which everyone stops thinking. So I hate jargon. But science communication is much better at communicating between different worldviews and different ways of thinking and different value systems and evaluating that. Science is much better at just measuring it and seeing whether it works or not. In science, we sort of have the language to describe the problem. And in science communication, we don't really. We just go, oh, it's complicated, it's not got a narrative, we can't talk about it. And even when you hear complicated things being talked about, unless it's a very long book, they're broken down into these little stories. And science communication is much more collaborative. So I think there are lessons from both. So I think there's no right answer to this. Especially when it comes to the ethical stuff that I didn't talk about. But it's very important to know, to be aware of the landscape. I think this is the case for a lot of these difficult problems. It's not about saying, here's the recipes to get to the right answer. It's about going, well, there's a map of a landscape, and I'm going to be somewhere in that landscape, and I just need to know where I am, so I'm aware of what I'm doing, because that prevents you making the mistakes that stuff everything up. So I think this is why I talk about this, because I think we should be aware of these landscapes. We should talk about them openly, and we shouldn't be afraid of the idea that they're difficult. This is really, really difficult. Both sets of complex systems are stuff our brain just doesn't want to know about, and yet that is the reality of how the world works. And if we want to tell the public why they convince science, why they should fund science, we have to deal with that. So I think we should talk about it openly. I was at Churchill College in Cambridge. I like Churchill. He said many very funny things, and occasionally he said things that were very accurate. I like this one. A pessimist sees the difficulty in every opportunity, and an optimist sees the opportunity in every difficulty. And I think this is an opportunity, especially in the age of the internet, but only if we face it head on instead of running away from it. And at the moment, it's uncomfortable. No one wants to do it, so no one's really doing it. So that's the end. I've probably just about got to the end of my time slot, but that's it. Thank you for coming.
My apologies both to you and to Helen for the slow start to the proceedings, and I'm afraid that means that we don't really have time for any questions, because we do have to leave. But with the Paris meeting in the offing, we've been treated to a very topical lecture and a very interesting and humorous one. Thank you very much, Helen.